Alright guys, welcome to lesson 8.7. We're going to talk about another useful exponential function called the continuous compounding function. It's based on a number called Euler's number. So we're going to learn about what that number is first, and then we're going to learn how that number is used to create that special type of exponential function. Alright, let me raise this up a bit so you guys can see a little more. Suppose you invest $1 at an annual rate of 100% for a year. Complete the chart below to determine the annual rate for each compounding scenario. So, annually means once. So, we're compounding it only once. We're investing a dollar with a 100% interest rate. What it would look like is this. My starting amount is 1. And then we have parentheses 1 plus my R value. If you divide 100 by 100, you get 1. It's compounded once a year, so I put a 1 here. And I also put it here, and then we're going to do that only for 1 year. So I've got 1s everywhere. Seems kind of silly. We can simplify that pretty easily, though. It comes out to be 2. But what if I compounded it quarterly? Well, you guys might remember from our lesson last time that well, first of all, it'll look like this now, right? We're going to have a 4 here and here because our n value is different. But you also are going to recall that the number that we get as a result of that is going to be a little bit more than the one before it, because the more you compound it, the more you get. And what if we did monthly? That would mean 12 times. Well, at that point, we would have that much. Now you're noticing it's not growing very much, right? It does get bigger, but not by a lot. Like from here to here, it went up by about 0.4-ish, right? And then from here to here, it only went up about 0.2 more, right? So it is increasing, but it's increasing at a slower and slower rate. Let's take a look at the next one. Let's say if we wanted to compound it daily for a whole year, that would be 365 times because there's 365 days in a year. So let's take a look at that. Wow. So barely any difference at all. It went up by 0.1. Let's take a look at hourly. So how many hours are in a year? Well, there's that many, right? So if we do that, we're going to get that. And then finally, what if we did it every minute? I mean, you could just do this more and more every time. But as you kind of see, it's still growing, but it's growing slower and slower. Like here it went up 0.4, here it went up 0.2, here it went up 0.1. And here, to get from here to here, it only changed by 0.004. And then from here to here, it's 0.001, 0.0001. So it's increasing every time, but at a slower and slower rate. And what that means is it's going to eventually reach a limit. The more you do this, the more it's going to reach a limit. Now, something very interesting happens here when you just let this number go to infinity. And you get a number that looks a lot like this. It barely looks any different at all. But it has an exact value that mathematicians have figured out. And it's very, very close to this. But they, instead of writing the whole thing out, which you actually can't, it's like pi. It goes on forever. They gave it a name called E. And that's what we call Euler's number. Okay. And what's interesting about that as far as what we've learned so far is that whenever you compound something an infinite number of times, you get the greatest possible output from your compounded interest formula. So E is the number that results from your greatest possible output. So I want you guys to watch a little video about that. This guy is going to tell you some interesting things about E before we go any further.
Because E is the natural language of growth, and I'll show you why. Okay. Let's draw a graph, y equals e to the x. So we're taking powers of e. So here at 0, this would cross at 1. So if you took a point on this graph, right, the value at that point is e to the power x. And this is why it's important. The gradient at that point, the gradient of the curve at that point is e to the x. And the area under the curve, which means the area under the curve all the way down to minus infinity, is e to the x. And it's the only function that has that property. So it has the same value, gradient, and area at every point along the line. So at 1, the value is e, because it's e to the power 1. The value is 2.718, the gradient is 2.718, and the area under the curve is 2.718. The reason this is important then, because it's unique in having this property as well, it becomes the natural language of calculus. And calculus is the maths of rate of change and growth and areas, maths like that. And if you're interested in those things, if you write it in terms of e, then the maths becomes much simpler. Because if you don't write it in terms of e, you get lots of nasty constants, and the maths is really messy. If you're trying to deliberately avoid using e, you're making it hard for yourself. It's the natural language of growth. And of course,
so there you guys have it. That's a little introduction to Euler's number E. It's about equal to 2.71 is an approximation. It's like pi. It keeps going on forever and ever, and there's not an end to it. But we're just going to go ahead and estimate it with about 2.71. Okay. It's the result of continuous compounding. What do I mean by that? Well, we've been doing compounded problems, right, where you compound it 4 times or 12 times. But what if you just compound it an infinite number of times? In other words, continuously. It never stops compounding. Then you end up with getting E out of it. So if we take our little formula here, our compound interest formula, and we let n, the number of times we're compounding it, go to infinity, it becomes this new formula, which is written like this. A equals P E R T. Now, I'm not going to show you how they get from here to here, but it does have something to do with letting n going to infinity. And so we have our new special exponential formula here. We talked about this special one last time. That's for compound interest problems. This is another special type of compound interest formula where it is compounded continuously. In other words, this is the one that will give you the greatest possible output. Now, so why do we care about this? Well, aside from the fact that it gives you the greatest possible output, as the guy in the video was telling you, has some very interesting property, which are evident in calculus. Calculus is a math which is all about slope, which in calculus we call it the derivative, and it's also about area, which in calculus we call the integral. And as the guy in the video pointed out, what's really interesting about the function e to the x power is that at every point along the curve, the y value, the slope, and the area under the curve are all exactly the same. And because of that, you end up with really nice solutions when you work with e to the x in calculus. There's other exponential functions like 2 to the x, but when you start trying to find its slope and area, you get some pretty messy looking answers. But if you're doing e to the x, you already know the answer right away. You don't even have to do any math. It's just e to the x is the answer. So e to the x is really calculus friendly. That's why another reason why it gets some special attention. Something else that can be helpful is, let's say you do have a function that's not written as e. You can actually change any number you want to into e. For instance, if I had 4, I could change that into 2 to the second power, right? Well, it turns out you can also write e to some power does in fact equal 4. So you can actually change any number you want into e, and by doing that, you can get to that place where you have that nice calculus type of problem. So you can write any number in the form of e to the r. So here's a couple of examples here. E to the 2.198 power is 9, and you could try that on your calculator to test it. It's not going to be exact because this is a rounded number here, but it'll be really close to 9. E to the 0.406 power equals 1.5, and e to the negative 0.357 power equals 0.7. Okay, now can you guys notice anything different about this last one? It's got a negative power, right? These other two have positive powers. compare their answers. What do you notice there about the difference between the answer here when you have a negative power and the answer here when you have positive powers? Both of these numbers are greater than 1. This one's less than 1. And that's the kind of stuff we've been talking about with these exponential functions here. So notice that if the original number is greater than 1, like 9 or 1.5, then the r value, the exponent, r, will be positive or greater than 0. If the original number is less than 1, then the exponent, the r value, will be less than 1. I'm sorry, less than 0. Okay? So, and that's just another way of saying positive and negative, just so you guys know. Right? You can say r is positive and r is negative. That might make more sense to you if you write that instead of greater than, less than 0, whatever you prefer. But there it is. So this is our summary of information about this special number E, Euler's number, what it is, why it's special, and this is the formula we're going to be using today. So let's go ahead and jump into some other stuff. So here's our function. If an initial deposit is compounded continuously, that's your key word there, continuously, at an annual rate of r, the balance t years later can be calculated using this formula. Okay? And it's important to understand this. I'm going to draw an arrow, and I would encourage you guys to write this too. If the function is decreasing, that means that r is negative. Remember how we said before, if r is negative, you're going to have a number here that's less than 1, and that means you have a growth factor that is actually causing it to decrease. If the function is increasing, that means that r is positive. So that's a little note you might want to add on to your slide here. All right. I think we're ready to do some examples. All right, so this one says, this is example 1, by the way, if you want to title that on your notes as example 1. It says Cody invests this much money in a retirement account with a fixed annual interest rate of 8%. And here's a very important key word here for today, compounded continuously. What will the account balance be after 14 years? Well, since we see this word here, we know that we're going to be using this formula here. Okay, so let's go through and label all these. The P number is still the starting amount. The starting amount is $1,651. This number here is still going to be my R. So we just take 8 and divide it by 100, and we end up with 0.08 is going to be my R value. And it says, what will the account balance be after 14 years? That's our T, of course. And so let's go ahead and see what that'll all look like if we plug in all these numbers. We have the final amount is equal to the starting amount raised to the power of R times T. Matter of fact, I think I'll write that a little bit differently. Write it like this. All right, so we need to know how to put this into our calculator. Now, you could estimate this and just type in 2.71, but your calculator actually has an E button, and I'm going to encourage you guys to be using the E button. I would not estimate it as 2.71. All right, so the way we're going to type this into our calculators in the following way, we're going to type 1651 first, and then we're going to find the E button, and I'll show you where that's at, but we're going to want to get E, and then we're going to do the power button, which you guys know looks like this, and then in parentheses, we're going to put 0.08 times, draw a little star there for times, 14. Okay, now that's if you want to put it all in there at once. If you don't want to put it all in there at once, we'll show you another way to do that, just doing it in pieces. Once again, if you're going to do that, you're going to go with order of operations. but I'm going to go ahead and type it all in at once. So first of all, let's do 1651. Now, where's that E button at? Well, E is right. There's two E's on here usually. Sometimes you might only have an E to the X. Sometimes you might have just an E. I want just the E button here. It's not this. This is a capital E. That's different. It's this blue one. So I'm going to push second and then E. Now, where it's located out on your calculators, it's going to be hard to say. But just look around till you see it. And usually do you have to push the second or the shift button to get to it. So there's my E. Then we're going to find our exponent button, which is here. And then in parentheses, we're going to put 0.08 times 14. And then enter. We've got our answer. So that's my final answer there. Okay. Now, if you wanted to do all this stuff one step at a time, we're going to have to do order of operations. So the first thing you would want to do is you would want to start off with your parentheses. So I'd want to do this first. Okay, so let's do that. 0.08 times 14. Oops, I did 15. Let me fix that. So I get 1.12. So I'm going to come down here and I'm going to replace all of this with 1.12 then. I would still encourage you, even if you are doing it just in pieces, to make sure you're using the E button and not estimating it with 2.71, but you could. So let's do our E button now. I want to do this part now, which is E to the 1.12. So after parentheses comes exponents. So E to the 1.21. So second E to the power of 1.12. Enter. So there's that. And that's what I'm going to put here. After you do your exponent, you're going to go ahead and do your multiplication. And here I'm just going to have to cut it off somewhere. We'll go up to the third decimal place, I guess, there. So we're going to take that answer that we just had and we're going to multiply it now by, so I just pushed times and it takes the last thing that was in there, times the starting amount, 1651. So you do multiplication last. And there's the same answer, just got there a different way by doing it in pieces. So once again, whichever way you prefer is fine. All right, so let's have you guys go ahead and try one of these. All right, so we're going to call this Student Practice 1. This is number 4 on the attached worksheet. Go ahead and work this one out and pause the video here. And when you unpause it, I'll show you the solution. Alrighty, so here would be your setup, and here would be the answer, 14,921.35 approximately. All right, let's go ahead and do an example 2. All right, so example 2. Here we go. So find the problem on your worksheet. Number 2 says, Indiba invests a sum of money in savings account with a fixed annual interest rate of 7%. So there's my R value. R is equal to that number divided by 100, which is 0.07. Compounded continuously. After 9 years, the balance reaches that much. Now that's a final amount. And T is my time, which is 9 years. They want to know what's the initial amount of the investment. So we want to know, what does P equal? The starting amount. Okay, so in our A equals PERT formula, we know A is 2748.82. We don't know what P is. E is a number, so it's just going to be there. And then R is 0.07, and T is 9. So how are we going to solve this? Well, basically what I'm going to do is I'm going to figure out what this equals first on my calculator, and then I'm going to divide it over to the other side so I can get P by itself. So let's go ahead and do that. All right, so first thing we'll do is figure out what E to the power of 0.07 times 9 is. So we're going to do E oops, wrong button, e to the power of 0.07 in parentheses, I guess I should do. On my calculator, it doesn't actually matter if I use parentheses or not, but most calculators that you guys use in my class, it will matter. So I'll just stick with it for now. But e to the 0.07 times 9 equals this. And so what we have then is we have 2748.82 is equal to P times, I just figured out what all that was. It was 1.88 approximately. So now what I'm going to do is I'm going to divide both sides by that 1.88 there. Just like that. And that way on the right side these cancel and I'll have P by itself, and that way I'll know what P equals. Okay. So let's go ahead and figure out what this whole thing comes out to be on our calculator. We're going to have 2748.82 divided by this up here. Now you could just type 1.88 if you want to. But a lot of times you can see this thing that says ANS online. A lot of calculators will have this on there. What that means is whatever your last answer was, they'll put it here for you, so you don't have to type it or round it and lose your accuracy. So that's what I'm going to do. Since it's a blue lettered one above the button, I know I need to push second and then that. And that just basically transfers this number down here like that, and I can just push enter. If that's confusing to you, you could have totally just typed 1.88 and that would have been fine. But there it is. So that would have been the starting amount of money that we had in that particular situation. All right, let's go ahead and have you guys do a student practice for that one then. All right, student practice 2. So go ahead and pause the video here, and when you're done, you will see the solution. All right, so this is your setup, and then this up here is your final answer for that particular problem.
All right, so we want to determine if the following functions are increasing or decreasing. This is a review question, but then it kind of leads into something new, okay? So what we've learned in the past is that when you have a function of this sort, if b is greater than 1, then our function is increasing. And if b is less than 1, then it's decreasing. And just so you know, b has to be greater than 0. So when I say less than 1, I really mean between 0 and 1, right? So let's go ahead and take a look at these questions now. This is greater than 1, so this would be increasing. This is less than 1, so this would be decreasing. But here's where the new stuff comes in. What about when we have e involved? Well, first of all, it might be helpful for you guys to remember what e is. E is approximately 2.71. Now you might be thinking, okay, well therefore it's bigger than 1. Well, maybe. Hold on a minute. You notice there's a 2 right here. Okay? Now that means that you can basically move that into the parentheses. Let's put x out there though. And we can simplify this. 2.71 to the power of 2. Let me back up a little bit. 2.71 to the power of 2. Let me get my calculator. I'll tell you what that's about 7.3. So as you guys can see, yes, that's bigger than 1, and therefore this is increasing. So the first thing I did was I realized, okay, e is just 2.71, but then I got this 2, so that means I need to square it. So yes, I do end up with something bigger than 1. It's increasing. Let's go ahead and take a look at the other one here, though. This is going to be 3 times 2.71, right, to the negative 2x power. So you guys probably might already see where I'm going with this. That can be rewritten like this. Right? Now some of you guys know that a negative exponent, hopefully you guys know that means you make a reciprocal, right? And when you do that, you can make it become positive 2. Well, we already know what this equals, right? We know that that equals 7.3 approximately. Well, if you divide 1 by 7.3, that's clearly going to be less than 1, so this is decreasing. Okay, so we have a general rule here, and this is something I would like you guys to write down. If you have y equals a times e to the, we'll call it kx, if your k value is positive, that means the function's increasing. And likewise, if k is negative, that means our function is decreasing. Okay, so when you're working with e, the way you can tell if it's increasing or decreasing is whether or not your exponent is positive or negative. So knowing that, we're going to jump into another example here. So let's go ahead and take a look at example 2. Example 2 says caffeine leaves the body at a continuous rate of 17% per hour. How much caffeine is left in the body 8 hours after drinking a cup of coffee containing 100 milligrams of caffeine? All right, so first of all, we see this key word here, continuous, and that's our cue. We know we're using this formula here now, right? Continuous compounding, we're going to have this kind of thing. Now, it's not compounding. It doesn't use that word, but it is still a continuous rate. And anytime using continuous rate of change, we're going to use that formula. So let's identify our stuff. This is our R value, right? But there's a couple of interesting things I want to talk to you about this R. So first of all, we do divide it by 100, right? But here's something new. Here's something new. The caffeine is leaving the body, and therefore it's decreasing, and therefore we're going to make it negative, right? Because we said that whenever your value is negative, that means that your function is decreasing. All right? So there's that. Here's our time value, and here's our starting amount. All right? So let's go ahead and plug these things in here and see how this all works out. We have 100 grams of coffee. We are decreasing at 17% per hour, and that's for 8 hours. And at this point, we're just going to go ahead and punch this into our calculator and see what we get. Now, as you guys put it in your calculator, I would encourage you guys to type it like this. And it's important that you guys understand that there's a difference between the subtraction button and the negative button on the calculator. There are two of them. Typically, the negative button, which is the one we want here, that's at the bottom of the calculator. The subtraction button is the one on the side of the calculator. We want the negative button. So go ahead and type that in your calculator and see what you get. And I'm getting something about 25.667-ish, and that would be milligrams. So the point of the example is to show you that we've been using this formula so far today for compound interest formulas where the amount is increasing, and so our R value is always positive. But when functions are of this form, if the R is negative, it means it's decreasing. Okay, so when we have a word problem where your amount is decreasing by a certain amount, you're going to set it up the same way. It's just that you need to remember to make sure that your R is negative. All right, so I'm going to throw one of these at you guys, see how you do. Go ahead and pause the video here and try out student practice number 2. When you unpause the video, you'll see the solution. All right. So there's our answer for that one. Here's your setup. The starting amount was 7.3. The R, 2.2. If you divide that by 100, you're going to get 0.0022. And since it is decreasing, we're going to make that rate a negative rate. And then that's going on for 2 years. So when you plug those values in the appropriate spots and then into your calculator, you should end up with about 6.986 million people there. So that's that. Let's go ahead and move on to another topic involving E. Now, you don't need to write down this slide here. I just want you guys to remember this. We've done graphing exponential functions before, right? A plus C tells you your y-intercept. C is your horizontal asymptote, and then you use the chart. If A is positive and B is greater than 1, it looks like this. And if B is less than 1 with a positive A, it looks like that. And then if your A value is negative, it takes these shapes and it flips them upside down, right? So that's old news. We've done that already. But I want to talk about graphing with E. So let's get into that. So graphing exponential functions that have Euler's number. All right? Well, the first two steps are actually identical. So when you see something that looks like this, your y-intercept is still going to be A plus C. Okay? Your horizontal asymptote is still going to be this number. All right, but let's get into the graph and the shape of the graph here. We've talked about how if this is a positive number, that means that your function is increasing, right? So if you have a positive A value and K is a positive number, that means this is bigger than 1. Your graph is going to be going upwards because your graph is increasing. Whereas if K is negative, that means that your graph is decreasing and it looks like this, right? But, once again, if the A is negative, that flips everything upside down. So, if A is negative, your graph will go downwards like that. Or, in this case over here, it will go upwards. So, there's our shapes. Now, something I want to point out to you is that this K, if it's negative, sometimes they'll write it in a way that makes it look more like a fraction, and I'll show you what I mean on the next slide. So let's go ahead and do an example problem here. We want to graph them. Now, the last time we graphed, I told you find the y-intercepts, write down the horizontal asymptotes, do the end behavior. We're not going to do all that fancy stuff today. We still have to do the horizontal asymptotes and y-intercepts, but we'll kind of just do it in passing because we've already got that stuff down. So let's begin here with example 1. First of all, what is my y-intercept? It's going to be A plus C, right? So negative 3 plus 2 is negative 1. So I'm going to put a dot at negative 1 on the y-axis. What's my horizontal asymptote? It's this number here. So positive 2. All right. Now we're ready to graph it. Right, so let me go ahead and clean this up here a little bit. So on our chart, we need to look at A and K. Okay, so my A is negative, right? And my K value isn't there, so that means it's a 1. And that's a positive. So look at your chart and see what the shape should look like when you have a negative A and a positive K. It should be the one that is flat on the left and going down on the right. And there you go. Right? Let's go ahead and take a look at another one. Let's go ahead and do number 2. What's the y-intercept? There's no A, that means it's a 1, right? So we have 1 plus 4, which is 5. So let's plot that. Horizontal asymptote. That would be this number right here at y equals 4. Now we're ready to graph it. So let's observe what our A and our K are. So once again, my A is 1, so that means A is positive. And let's look at our k. Our k is negative 2, so that's negative. Look at your chart. Look for the spot where a is positive and k is negative. And that's the one where you'll find that it should be flat on the right side and then going up on the left side. And that would be our exponential function for that one. Okay, now number 3 is an important one for you guys to pay attention to. The software that I have doesn't usually write it like this. It writes it like this. And I'll show you what we're talking about there. You'll notice that that's a fraction, right? Well, what that means, you guys, is that means we have 2e to the negative 1x. Why are these the same thing? Because as you guys know, negative exponents make reciprocals, right? So basically what I want you guys to know is that this is the same thing as this. That's important. And therefore our k is negative. And that's going to come in handy as we work on it. So you will see it written like this on occasion, 1 over e. That's the same thing as saying e to the negative 1, and therefore k is negative. So keep that in mind. But with that having been said, let's go ahead and do the problem. So you'll notice that we're missing our c value, and when that's missing, that's a 0. So what is my y-intercept? A plus c. So my a is 2, my c is 0. So 2 plus 0 is 2. So it's touching the the y-axis at 2. What is my horizontal asymptote? That would be this number over here, which in this case is 0. So we have our horizontal asymptote is actually going to be right on the x-axis. Now we've got to figure out our shape. Now, as you guys can see, my a is positive. And as we've already said, since it was written as a fraction, that really means that k is negative. And now we're going to look at our chart and find where a is positive and k is negative. We're going to find it's this one. Okay? So, there you guys have it. So that's how you can graph functions that have an e in it. Go ahead and let you guys try a couple of these. Go ahead and pause the video. When you unpause it, you will see the graphs for these 4 functions. All right, guys, so here are the solutions. So for number 1, you'll notice that we don't have our a in place or our k, so I rewrote it like this. Both the a and the k will be 1. Y-intercept is 3. Horizontal asymptote is 2. And since the a is positive and the k is negative, the shape would look like what you see there. On number 2, we don't like it being written like this, so I rewrote it like this. And now we can see that the a is negative and the k is negative. We have this shape as a result, with a y-intercept at 1 and a horizontal asymptote at 5. And on the last one, we're missing some numbers, so I rewrote it like this. The a is 1, the k is 2, and the c is 0. So my y-intercept will be 1. My horizontal asymptote is the x-axis. It's right at 0. And since my k is positive and my a is positive, the shape will be what you see there. Right? And so that's graphing with exponential functions that have Euler's number in it. And then just so you guys know, your problems will either look like this or they'll look like this. The software that I have will not generate them having negatives here. I prefer that strategy, but this is what they'll look like. So just so you guys know, whenever you see that 1 over e, that means that your function will be decreasing on those intervals. Okay, so that's that. We'll end it there, and we'll see you guys in class. This is just a nice little summary, by the way, of the different special formulas we've looked at and when to use them. But we'll get to that again when we do our study guide. So we'll see you guys in class, and have a good day. Bye-bye.